All right. Welcome to another BIMSA member seminar. It's an honor to have Professor Anton Dzhamay. He's an associate professor in BIMSA in the representation theory and mathematical physics group, and he's going to talk about what is a discrete Painlevé equation.
Thank you, Anton. Thank you very much. It is a pleasure to give a talk at this fun seminar. So my research field is integrable systems and partly the use of geometry in integrable systems. And for the last maybe 10 years, I've been interested in this particular class of integrable systems or dynamical systems known as discrete Painlevé equations. And my one goal for today is to give you some sense of what this object is, because the name actually may be slightly misleading. In particular, it suggests that this is an equation, which it's actually really not. Okay, so I think fundamentally, a discrete Painlevé equation is a particular example of two-dimensional, integrable, non-autonomous, discrete dynamical system. And I will try to explain all of these words. But the right way of thinking about it is as an element of infinite order, so-called quasi-translation, in certain collection of affine Weyl groups. And it's also, the name comes from the relationship to differential Painlevé equations, but in a way, discrete Painlevé equation is a more fundamental object. And this is what I will not talk about. I will not talk about all the interesting applications of discrete Painlevé equations, because there actually had been a number of talks at this seminar, including the talk last week, that actually are related to areas where these equations appear. In particular, they appear as sort of a discrete counterpart to differentiable equations like Painlevé equations in questions in integrable probability and in theory of orthogonal polynomials. For example, discrete Painlevé equations often govern the following. When you have orthogonal polynomials, there is something known as a three-term recurrence relation, which tells you how you can get a polynomial of high degree by multiplying by x and subtracting something. The coefficients of this something as functions of a degree often are governed by discrete Painlevé equations. Okay, and of course, I hope that you will at least slightly agree with me that this construction is a very elegant and beautiful construction. So let's begin. I will start in a very general setting of a dynamical system. So roughly, a dynamical system is you have a certain space of states known as a configuration space. And on this space of states, you have some kind of evolution. So you have a physical system, and you want to know how it evolves in time. And you can define evolution, for example, by specifying some vector field, and then your evolution will be an integral trajectory of this vector field starting at some initial state x naught. What about discrete dynamical system? Well, as a preliminary step, you can think about sampling your trajectory at small time intervals. Take an epsilon mesh on your timeline and see where you are, let's say, every 5 seconds. So you can think about it like this. This is your initial step. This is state. This is your state 5 seconds later, 10 seconds later, and so on. And to get to the nth state, there are two ways you can think about it. First, you can make n steps in time. Or second, you can go to the xn minus 1 state and then do an epsilon step. So what this means is that you can actually get to it by iterating this one-step function, but changing the initial position in this function, so the resetting initial condition. So then you can generalize from this underlying differential equation to a purely discrete case, where you just have some function on your space of states, and you have a discrete trajectory that you get by iterating this mapping phi. Start at initial state, then apply phi, get to x1, apply phi again, get to x2, and so on. So that's a basic setting of discrete dynamical system. And usually people working in this area are interested in chaotic systems and growth of entropy in things like fractals. But I'm interested in what is known as an integrable case and also non-autonomous case. So how can we think about non-autonomous discrete dynamical system? What does it mean? So usually when you have a physical system, it's non-autonomous when the total energy, say, of the system changes as a function of time. So here we can do the following. As a sort of a preliminary step, we can look at the extended phase space of our system. So we add an extra timeline. So here my time is an integer n. So I assume that I can go both forward and backward. And then just create copies of the configuration space. And think about phi as not going from x to itself, but rather also making this motion in time. There is a standard notation here where current state xn is usually denoted simply by x, and the future state is denoted by x bar, not to be confused with complex conjugate, and previous state is x underbar. When you have lattice equations, you can change bars to heads and tildes, and notations get interesting. Okay, so non-autonomous part. Let's add a parameter space, and let's make our configuration spaces not a fixed space, but a family of spaces, parameterized by these parameters. And we will see in the example on how this is done for Painlevé equations. Also, your function, your mapping, will depend on the parameter, okay? And the requirement is that if you have a really dynamical system, there should be some kind of translational motion on the parameter space that you may lose on this level because you can go through some nonlinear maps, but there's some translational thing underlying it. And I will begin by showing an example of a non-autonomous discrete system known as a QRT map. QRT stands for Quispel-Roberts-Thompson, who discovered this class of maps in studying discretizations of some soliton equations. But the construction itself is very, very beautiful and simple. You do the following. You take a plane, and on this plane, you take a curve whose equation is quadratic in variables x and y, where x and y are some coordinates on this plane. The nice thing about it being quadratic is if you fix a point and then fix an x coordinate of the point, this becomes a quadratic equation in y, and it will have two solutions. So you can do this kind of involution. For that, of course, you need to work over complex numbers. And because we will have families of such maps, you want to make sure that if your quadratic equation degenerates into linear, you still have two solutions. That's why you projectivize. So my preliminary configuration space would be just complex projective line times complex projective line. And in terms of topology, it's just a sphere times a sphere. Then you take this curve, and you have x involution, y involution when you fix x, and can go from this point here in y, or you can do x involution when you fix y and go to this point in x. By themselves, involutions are maps of order 2. That's actually related to the fact that we will eventually be talking about affine Weyl groups generated by reflections. But what we can do is we can take the composition of these two involutions. And we get this mapping that I will call eta. And sometimes it's possible to look at half step, because to do this involution in x and y, you can do involution in y, then change coordinates x and y, do involution in y again, and change coordinates back. there's some technicalities. This matrix will get transposed, but modulo that. Often you have what is known as a half step or the square root of QRT. Okay, so that's the construction. And here is how it looks like. And I don't understand why it's doing that. Okay, so let's see. Yeah, that's what I was trying to do. Okay, so here you see that we're doing y involution, x involution, we get this point. Okay, do it again, do it again, do it again. You get this nice kind of motion. Okay, now if you look at the initial map, if you look just at this curve, without too big of a stretch of imagination, you can think about it as if you have a torus and slice it. And that's indeed what's happening here, because generically a biquadratic curve on P1 cross P1 is an elliptic curve. So this, what you see on this picture is just a slice of a particular elliptic curve known as a Linus curve. And this is the dynamics. And the dynamics really is a translation on some vector on this curve, on the elliptic curve. So it's an abelian group structure, very nice and simple map. Kurt? I don't know if, well, right. So you're probably talking about the real slice. That's right. I'm talking about biquadratic. Yeah. Okay. All right. So this is a dynamics on the curve, but I want a two-dimensional dynamics. Okay. So I want to extend this mapping from the curve to the whole plane. And the way to do it is, rather than one curve specified by a matrix A, you take two curves specified by matrices A and B. Okay? And then you can construct something that is called a pencil or a one-dimensional linear system of curves. And such a pencil will foliate your plane. And then you can do this dynamics on any point. Say you start on the point here, and there is some curve from this pencil going through this point. Then you just do your mapping on this particular curve. Okay? In particular, notice that this is an integrable system because you conserve the curve. You stay on the curve. But there is a problem. And the problem is here. These are the points where the curves A and B intersect. Okay? So what's happening then is if both equations become 0, then any equation in this pencil is 0. So all curves in this pencil will go through this point. So what happens is, suppose that at some step in your dynamic, you land at this point. It's like before that, you were following this narrow path through the forest, and suddenly you're in the middle of a city square, and you have all possible directions that you can go. Okay? So on the level of equations, what happens is your equation becomes undefined. Okay? But this picture suggests the fix. And the fix is you just do the blow up at this point, which is a surgery. And here is an attempt to indicate what this surgery is on the real picture. But of course, we're working in the complex world. So the idea is you introduce an extra vertical dimension, and you lift the curves according to the slope at which they enter the point. Okay? It can be done as a coordinate transformation. It can also be done as a surgery where you take the point out and instead glue in a sphere. And the sphere is this line of slopes known as an exceptional divisor. at this point. So you change geometry of your space to fix the problems in the dynamic. Okay? I want to introduce a little bit of notation here. So away from the central point, we have a bijection, but the central point, every curve goes through. So if you want to take a preimage of a curve here on this space, you will always pick up all of the exceptional divisor E, the central fiber. So M minus E is called the proper transform, and it's just that curve that we have here. Okay? So we do that, and there's something nice happening. First, dynamics is now completely resolved. Okay, you have an automorphism of this resulting surface X that you get by doing this blow-ups. Of course, if you blow up a point, you have to extend the dynamics, which is not difficult because it's just a change of coordinates, and rational maps you can easily extend. However, there's no guarantee that you do not get more bad points. But here the process is finite, and we get this rational elliptic surface. And the reason for these words, rational and elliptic, is first, it's birational to P1 cross P1 or to P2. And there is this vibration by our pencil over base of P1, where this is the parameter lambda of the pencil, and this is the curve corresponding to this lambda. So that's an integrable system. You have a conserved quantity. Okay? So this is the QRT map. There are some interesting objects associated with it. First, everything is explicit. There are explicit charts, and we work in explicit charts. Second, your dynamic can be, in a sense, linearized. There is a natural object here known as a Picard lattice or a Picard group. Its definition in general is the classifying space for line bundles, but here you can identify it with second homology or second cohomology with integer coefficients, or just with the divisor class group. And in particular, if you think about the structure of this on P1 cross P1, there are two generators. You can think about them as classes of each of the coordinate spheres. And every time you do a blow up, you do this bubble, and you add an extra generator to this lattice. It is also equipped with a structure known as an intersection product, where two coordinate lines, hx and hy, intersect at a point. Hx does not intersect with itself, because if you take, for example, two vertical lines, you can do the general position argument, they would be parallel. That's different for P1 cross P1 from P2. On P2, any pair of lines will intersect, like parallel lines will intersect at infinity, but on P1 cross P1, this is not the case. These exceptional classes have this property that their square is -1, whatever that means. How many, whatever the number of points. In this case, it will be 8, but it can be more. And
so can I ask? So you have this dynamical systems. What does Picard tell you?
I'll tell you.
Okay.
So you have the linearization of this mapping on the level of cohomology. So for QRT, it doesn't tell you much. Okay. And now I want to look at this. Sorry. One more thing that I want to say. There are canonical and anti-canonical classes. Canonical class is just a class of a top form. We're on a plane, so the form is dx dy up to a function, but the linear equivalence relation gets rid of the function. If you rewrite it with this chart at infinity, so little x is 1 over capital X, this coordinate is centered at 0, this coordinate is centered at infinity, you have two poles appearing. So the class of a the canonical class is two poles in the x variable, two poles in the y variable. And every time you do the blow-ups, there is an extra class appearing here. So anti-canonical or dual class is the same thing with a negative sign. Okay? And then our curves, this is what biquadratic is. Okay? Biquadratic curve is in the anti-canonical class on P1 cross P1. If you square it, you get 8, and that's where 8 points are coming from. And after you blow up, you get a square equal to 0, which means that generically there is a unique curve going through these 8 points. And then the curve will be in this class. This subtraction means that the curve was going through the point of the blow up. And we're talking about the class of a proper transform. QRT case is special because the 8 points that we gotten, we didn't just pick them up. We took 2 biquadratic curves and intersected. That already creates this linear system. And here's the idea. To go from QRT to discrete Painlevé, you take points and push them. Okay? So I'll show it by example. And this is an approach that we followed with Tomoyuki Takinawa from Tokyo and Stefan Karste from Bucharest. So discrete Painlevé equations were originally obtained, like large number of examples were obtained by Basil Grammaticus and Alfred Romani by doing something called deautonomization of QRT, but they did it on the level of equations, and we wanted to understand geometry. Okay, so here's a particular example that I want to use. This equation is known as discretization of a NAM equation, if you want a name, but whatever. Just some mapping. This mapping is in the QRT family. And you can see the base points of the mapping. For example, when x and y are reciprocal of one another, numerator will vanish. And if you want the numerator and denominator to vanish simultaneously, you can take x to be square root of 2, y to be 1 over square root of 2, and you get 0 over 0. Okay? This is the corresponding pencil. And when you look at the pencil of elliptic curves, they're generic fibers that are really elliptic curves, and they're singular fibers. So for this mapping, we will see that singular fibers will look like this. So for example, here you can have 4 components, each of which is like a complex projective line intersecting like that. So these singular fibers were classified by Kodaira, and you can describe this classification in terms of these labels, and these are labels for something known as affine Dynkin diagram. Okay, so here's an example. So these are the base points. Okay, so what are the singular fibers? Well, for example, you can see that there are 2 straight lines going like this, right? And there are a few more. So let me show you. Okay, so here's one example. So this is one singular fiber. It has 3 components. And this is the equation, xy times xy minus 1. This is the example that I would look at. But then there is also this singular fiber, and this singular fiber. And everything else is elliptic. And what I would do is this. So here's my fiber, xy minus 1. These are the base points. And I pick up some generic point. Then there is a curve in the pencil, this orange curve, that goes through this point. And that would be my QRT curve for this dynamics. I'm showing you here not the full QRT map, but a half QRT, whose expression is given here, and then you iterate. Okay? But you can see the dynamics. It stays on this orange curve, that's conserved quantity, and does this kind of a thing. Okay? So what I want to do to go from here to discrete Painlevé is shown here. Do you see? I push the points a little bit. This purple points. So now the orange curve and this point, it's just a copy from here. This is just for the reference. And here is our dynamic. The blue one is a new one. So you see, it's off the curve, but there is something else happening that you may notice. Do you notice anything interesting happening here? So, do it again. If you look at the purple points, do you see that they start oscillating? That's the non-autonomous system. So what happens is the parameters of these points, they still stay on your chosen fiber, but they move on this fiber. And every time you blow up, you get a different surface because the points of blow up change, and it's not necessarily true that two such surfaces will be isomorphic. Those actually will be by the Painlevé map, but in general, it's not true. So, and then your equation becomes something like this, that comes back here in the autonomous limit, and parameters in this equation are related to coordinates of the point, and they evolve. So that's how you can think about discrete Painlevé equation. That's like one easiest way to see it as an example. There's quite a bit more here, and that comes back to Artan's question. The moment you choose a fiber, this curve decomposes into irreducible components. These irreducible components, you can take their classes in the Picard lattice, and you get a surface sublattice of Picard lattice. You can look at its orthogonal complement, and turns out that it's also a root lattice. And in this case, it will be of type E6. And these two lattices, one is responsible for geometry, the other is responsible for symmetry. How is alpha responsible for symmetry? Well, associated to this basis of the symmetry sublattice, you can again look at the affine Dynkin diagram. And for this affine Dynkin diagram, you can create a affine Weyl group where each node of the diagram gives you a generator. Each generator is an involution, and dependent on whether the nodes are connected or not, you have some relations. You need to extend it by automorphisms of the diagram, but we will not worry about that. And there is a linear representation of this group on the Picard lattice that you can tensor with Q to make it a vector space by reflections in root alpha. And these reflections in root alpha fix delta. That's the sense in which it's a symmetry. And turns out that you can then take this linear representation on the level of cohomology and push it down to actually create maps, elementary maps on this surface family. This is known as a birational representation of this affine Weyl group, and it acts by isometries on the surface family. Delta J are the surface classes. And there's a reason the same symbol delta is used, because this delta is the anti-canonical divisor class, can be expressed in terms of this. There its components, but also can be expressed in terms of alpha. And then if you look at the map eta that you induce on the Picard lattice by your dynamics and look at how it acts on the symmetry root, you see that if you iterate this map, you get a shift in the symmetry root sort of normalized by this delta, and you can represent it using generators, and that's what a discrete Painlevé equation is. So you can say that an abstract discrete Painlevé equation is a triple: geometry, orthogonal complement of a symmetry, and a word in the generators that give you a translation direction. And if you think about it this way, you can then step away from complicated equations and have very clean and nice representation, and it sort of explains why everything is quite algebraic. Okay? So this was the main part of my talk, and I want to say a few words about the history. Where does the name come from? Very briefly. Huh? These W's? They are, so you have reflections in roots. This is the map on the level of Picard, but you can push it as a map on the level of a surface. So that's what they are. Okay. So why Painlevé? So it goes back to the work of Paul Painlevé and his colleagues. Painlevé was famous not just as a mathematician, he also was a successful politician and a prime minister of France twice. But He was interested in something, in whether you can talk about purely nonlinear special functions. You can think about special functions, even like exponential function, as a solution of a differential equation. And that's how classical special functions like Airy, Hermite, Bessel come from solutions of linear second-order differential equations. What if equation is nonlinear? They're movable singularities, singularities that depend on constant of integration. And when you have singularities called poles, we can deal with them, just projectivize or compactify. But if you have roots, you have branching points, and moving branching points is a deal breaker. So Painlevé property is when this doesn't happen. And Painlevé equations are second-order equations that have this Painlevé property. Their solutions appear in random matrices, integrable probability, the limiting behavior of Young diagrams, et cetera, et cetera, et cetera. For example, the Tracy-Widom distribution is expressed in terms of a particular Painlevé transcendent. And these are the 6 Painlevé equations. This is like a classical theory that sits in this cascade. Now, discrete Painlevé equations, the name was coined in this paper by Itz, Kitaev, and Fokas. And really what they had is they had some nonlinear recurrence of which they took a continuous limit, and they got a discrete got differential Painlevé equation. So it was natural to call this a discrete analog of Painlevé equation, and it was a preliminary definition. So different equations that have limits to differential equations. And as I mentioned, a lot of examples were constructed by Grammaticus and Romani, but this is how they look like. This is known as DP1, and this is known as alternative DP1, meaning that they both have continuous limit to Painlevé 1, but otherwise are completely unrelated. Whereas this is known as DP2, and definitely looks a lot more like DP1 than this one, but it has continuous limit to DP2. So this was a very confusing scheme. And soon after, Japanese mathematician Hidetaka Sakai, following this Japanese school geometric approach to Painlevé equations, reformulated everything in terms of algebraic geometry. Then you get this beautiful classification scheme of all possible configurations. Differential Painlevé equations sit here. This is the cascade we saw before. And yeah, there are 2 more somehow. I also indicated here some examples of orthogonal polynomials that appear. Okay, so this kind of weights is related to this type of Painlevé equations. You also can see why there are different examples of DP2, because there are these 2 different degenerations. The example we looked at today is over here. And these are other examples that you can get from the same QRT map, but nothing else. So that was part of our motivation, is to understand, given QRT map, which Painlevé equations can you deautonomize it to and how. So I think it's a good point for me to stop. Thank you.
All right, questions? So I ask you some questions. First of all, in that picture that these points were wiggling back and forth, so some of these points are getting out of those curves, but this is natural.
No,
right?
No, they stay on. Well, depends on which curve you're talking about.
So I mean, the points are still on the surface, and basically.
So if you look here, right?
Yeah.
So the curves are the blue curves. The orange curve is just comparison with the
exactly.
QRT map.
So we don't worry, right?
So
it doesn't need to be on the orange curve at all, because now you have blown up the surface.
No, the orange curve is a stationary curve.
Yeah.
So it only exists if we put the points in this particular position, in the pencil. If you push them away from the pencil, but keep them on these blue curves, this is my chosen special fiber, they will stay on this special fiber, but they will wiggle. And other curves, there are no more sections in the pencil. There's unique section. So you can see that all the purple points, they move, but they always stay on blue curves.
Yeah.
Okay, some points are fixed because there is some residual normalization, but
okay. Another question: why is it that, I mean, probably is it that we should only look at these systems where any singularity comes from geometry? Because this vector field itself could be having singularities. Let's say you are looking at the flow field of some meromorphic function.
I'm not saying that this is all there is. It's a particular class.
But I want to know, is the assumption in Painlevé equations that the flow field that you have is only getting singular if the geometry of the surface becomes singular? Or can it be that I start from a meromorphic function, look at this flow field? That's my question.
It's a different question. It's more question to differential equations, the way you're phrasing it,
That's right,
than discrete equations. And that's actually how Okamoto's work started, where he was trying to look at differential Painlevé equations that can develop singularities like poles. And that's where the reason for projectivization, to account for initial condition that is like a pole for the solution coming in. But then you need to do quite a bit, because the moment you start projectivizing, you get some trajectories that stop flowing in time but flow in space, known as vertical lives. You need to throw them away, and that's exactly this IT-canonical divisor that we're looking at. Other type of singularities people look at, but these techniques don't work very well.
Okay. More questions if you have any? Yashik?
Can you go to the last slide, please? Can you explain who is in the root? Who is in the root?
This?
A10, yes.
Yeah. So think about 8 points on an elliptic curve.
I can do this.
So that's it.
Thank you. Maybe a little bit more details? Maybe some details? How dynamics looks like?
Oh, the dynamics is hard because the symmetry group there is the largest one. It's affine E8. So to write down an explicit expression for elliptic Painlevé is difficult. Formulas get difficult, and even a word in the group becomes long. How about I explain this a little bit more? So you start with 8 points on an elliptic curve, and you degenerate elliptic curve by pinching sort of one of the, is it a meridian or parallel? I never remember. Meridian.
One of the cycles.
Or actually do 2 or 3. And then you start getting configurations in here. Okay? So you start with 8 points on elliptic curve, start degenerating the curve, and then you fall into this whole classification. And this classification actually mirrors Kadarek's classification of exceptional fibers of elliptic surfaces. Okay?
And if you did this on surface?
Huh?
If you did this on surface, algebraic surface?
Well, I mean,
this
is a surface, right? If you,
no, yeah, but your classification is singularities of the elliptic fiber. So what
right.
if you did
But my configuration space is a surface.
Yes, so I'm saying, what if configuration space is a threefold and you did it on algebraic surface?
It's harder. So there are some works on doing higher order examples of Painlevé equations. There is classification of 4-dimensional Painlevé equations related to isomonodromic approach for linear systems. And there are some attempts to do the analog of this, but then you go from Picard to Néron-Severi, and the examples that I've seen are essentially 2-dimensional times 2-dimensional rather than genuinely 4-dimensional. There are various generalizations that people are interested in, including non-commutative version, quantum version. There is a very interesting and way too difficult for me preprint by Eric Rains and Andrei Okunkov, who do non-commutative Painlevé equations on non-commutative surfaces. So there.
Questions, if any?
Maybe a naive question. Is it possible to write the discrete Painlevé equation, means the recurrence relation, well, from one parameter to two parameter, which fix the parameter space of the elliptic curve? I mean, while we have xn with xn plus one a nonlinear relation, is that possible to write x and y and becomes a linear relation?
Let me answer it this way. There are examples of lattice equations, because that's probably what you're talking about, that have reductions to discrete Painlevé in some periodicity conditions, etc. Similar to how you can go from KdV equations, Kp equations to Painlevé in some ansatz, yes. If that was the question. But adding one extra parameter here, I don't see easy way to do that. Okay. We can talk, but it's...
Okay, thanks.
More questions?
You mentioned about orthogonal polynomials. It is well known the relation with Painlevé orthogonal, some special orthogonal polynomials. Are there some orthogonal polynomials for discrete case?
In which sense? In the sense of solutions?
Or, yes, special solutions for rational special solutions for
there. Yes. So
discrete Painlevé.
They're special solutions. They're not polynomials, though. They're some versions of Q versions of hypergeometric series,
but
or hypergeometric functions, for example.
But maybe this is not polynomials, but rational function.
Yeah, yeah.
By so rational.
There are some special solutions, but this this relationship is different. This relationship is probably the best way to think about that is in terms of a discrete version of Riemann-Hilbert problem, where on one hand you have orthogonal polynomials associated with a weight sitting on some nodes, and on the other hand you can rephrase that in terms of isomonodromy deformations or transformations of some deconnections, and the moduli space of such deconnections happen to be these surfaces that appear to Painlevé. So isomonodromy of deconnection is governed by Painlevé equations, and on the other hand, it relates to orthogonal polynomials as solutions of this discrete Riemann-Hilbert. But in terms of just solutions for discrete Painlevé, I don't think so. But I can double check.
Okay, let's thank Anton again.